So yes, before getting into the Powell's method for the Powell's algorithm, we are going to define two theorems. So yes, the first theorem states that given a quadratic function of n variables, okay, quadratic function means something like this. Yes, this function f of x1 x2. This function is a quadratic function. That means its highest degree is 2. Okay, not more than that. Of two variables x1 and x2. So here in this theorem we have given a quadratic function of n variables. Okay, n variables. So consider a quadratic function of n variables and two parallel hyperplanes 1 and 2. So what is hyperplanes? Hyperplanes are in geometry. A hyperplane is a subspace whose dimension is 1 less than that of its ambient space. That means, for example, let me consider the ambient space, a two-dimensional space, 2D space, and it is having this x1 and x2. That is two-dimensional space. Then the hyperplane means it is having a dimension less than 1. There is that less than 1. That means the dimension of the space is here 2. So the hyperplane is having a dimension 1. So one-dimensional space. Okay, one-dimensional space means your set of all straight lines in the two-dimensional space like this. It is stretching from minus infinity to plus infinity. So this is the hyperplane in a two-dimensional space. And in a three-dimensional space, having this x1, x2 and x3 coordinates, then the hyperplanes means, as its name indicates, the name fit for this three-dimensional space. Okay, so means it is having a dimension less than that of the ambient space by 1, that is 2. Okay, 2 will be the dimension of the hyperplane. That means it will be a set of all possible planes in a three-dimensional space like this, and it is extending from minus infinity to plus infinity. So such infinite number of planes we have, and in this here in a two-dimensional space, infinite number of hyperplanes, that is straight lines, we will be having. Okay, so such in a two-dimensional space, such straight lines are known as the hyperplanes, and in a three-dimensional space it is planes itself. Okay, and it is given that a quadratic function of n variables and two parallel hyperplanes 1 and 2, okay, h1 for example, h1 and h2 of dimension k less than n, okay, that we have defined, and we are considering 2 points. 2 points means 2 arbitrary points. That points are will be vectors x1 and x2, so points means nothing but your capital X1 and capital X2, which is will be a column matrix. Again, it is a vector. Okay, so yes, and then for example, in the case of a two-dimensional space, let me have the two-dimensional space like this. Two-dimensional space x1 and x2 like this, and we are considering two parallel hyperplanes. Two parallel hyperplanes means, for example, let this will be the first hyperplane like this, and parallel another hyperplane parallel to this will be like this. Okay, and this is 1 and this is 2. This is h1 and this is h2, and it is given that x1 and x2 x1 and x2 are x1 sorry, this is x1 and this is x2. X1 and x2 are two vectors or 2 points on these two hyperplanes. So what the theorem says, that the line joining x1 and x2 will be the conjugate direction to any line parallel to that hyperplane. That means the line joining x1 and x2 means like this. That means it will be x2 minus x1. It is directed in this direction. Okay, and this length is a conjugate direction. Is a conjugate direction to any such any parallel vector such that all these vectors are parallel to the hyperplanes 1 and 2. So I'm considering a number of vectors like s1, s2 and s3 like these, and s4, these vectors. See these 4 vectors, and these 4 vectors are parallel to the hyperplanes h1 and h2. Then, and also it is given that 2 points, 2 vectors on that hyperplanes x1 and x2, and the theorem says that if you join these two vectors with a line in this direction, with that is having a direction directed from x1 to x2, and this direction, that is we are calling s5. Okay, and this vector s5 will be a conjugate direction to all these s1, s2, s3 and s4, such that it will be having s5. Okay, s5 into a, the matrix a, sorry, s5, not s5, s5 transpose into a into s1 will be equal to 0, or s5 5 transpose into a into s2 will be equal to 0, like that. S5 transpose into a, s4 will be equal to 0. So this is the theorem. Okay, so that means if you want to find out the conjugate direction, okay, the conjugate direction to the vectors which are parallel to the hyperplanes h1 and h2, then you have to consider 2 points x1 and x2 in the h1 on the h1 and h2 respectively, and if you join these 2 points, and that direction will be the conjugate direction for these S1, S2, S3 and S4. That is what our first theorem says. Now the second theorem says that if a quadratic function like q of x equal to half x transpose into x plus b transpose x plus c, that is like your earlier example, this example f of x1 x2 equal to x1 minus, yes, this example, we have generalized that example with this matrix, that is half this capital X and capital AX, all these are metrics. So q of x, it is a quadratic function, and this quadratic function, if you have, you can minimize this quadratic function sequentially by applying the conjugate direction method. That means, yes, what in the univariate method, what we do is, if we have a if we have a quadratic function like this, then what we have done in univariate method, yes, this is the function f of x, f1, f2 of x, f3 of x, etc. So what we have done is, we have searched for the optimum solution by in two directions only, that is in x1 direction or in x2 direction or in x3 direction, etc. xn directions we have searched. In between we didn't search, right? But in this Powell method, we have defined a conjugate directions, so that we can search for the optimum solution in the conjugate direction also. And this conjugate direction, if you search, this theorem states that if you search in the conjugate direction, then the yes, the solution, optimum solution, you will get the optimum solution in a faster manner, or the convergency of this function will become faster. That means, yes, let me take this figure, okay, in which we have x1 x2 two variables, and f of x will be an objective function in objective function in x1 and x2, that is in two variables. So these are our functions, f of x, f1x, f2x, etc. Right. In univariate method, what we have done is, we have searched for optimal solution in the x1 direction, that is, we went in this direction first of all, and then we went in this direction, okay, and then then we reached in the point 3, where we got the optimum solution x3 star, right? In this manner we have searched for the optimality. But this, when if you, yes, by applying the theorem 1, okay, we will find out another feasible direction, that is joining 1 and 3 like this, okay, so that we can eliminate, we can we are not going in two directions, like yes, first we went in x1 direction and then we went x2 direction. Instead of searching in these two directions directly, in the next step we will directly go in this direction, that is in the very next search in the very next step from 3 we will go in this direction, okay, instead of going in this direction and then in this direction, okay. So this direction is nothing but your conjugate direction. conjugate direction. Okay, so in order to find that conjugate direction, we are defining this theorem 1, which says that uh, in order to find out the conjugate direction, you have to define two planes, hyperplanes, that's hyperplane 1 and 2. Okay, and you have to make sure that this x1 and x2, that is x1 and x2 means the optimum solutions x1 and x2 should lie on this hyperplanes, that is in this here these points, that is yes, in this example um yes, we have in this example, let me explain with this example. Yes, in this example, yes, in this example you have to define by theorem 1, you have to you should be provided with the two planes, that is hyperplanes, two hyperplanes h1 and h2. But here our discussion is associated with this two-dimensional space with axis x1 and x2. So our hyperplanes will look like straight lines. Okay, so that straight lines are this h1, yes, okay, extending from minus infinity to plus infinity, and another plane, hyperplane, is this. So h1 and h2. So you got h1 and h2 two hyperplanes, and also you have two optimum solutions. Optimum solutions. This is x1 and this is x2. So what the first theorem is saying that you join this x1 and x2. Okay, that is, and or x or you find out the length x2 minus x1, you find out, okay, x2 minus x1, which is directing in this direction. So that forms the conjugate direction. So that for the next search, you have to use this conjugate direction. Okay, so that I am using here in this direction, and I will get another optimum point here. Okay, so that is what your first theorem says. Now, yes, in that manner you can have conjugate directions. Okay, n number of conjugate directions you have, n number of conjugate directions we have. So if you go in all that n number of conjugate directions, the function q will be minimized, okay, at or before the nth step, irrespective of the starting point. That means whatever may be the starting point, okay, you will reach, you will have the minimum value of the function q, that is quadratic function, at or before the nth step if you go in the conjugate direction. Okay, that is uh, that means the theorem second theorem says that if a quadratic function given by q of x, that formula is minimized sequentially once along each direction of a set of n mutually conjugate directions. So you have to find n mutually conjugate directions, and then you search in that direction. Then the theorem says that the minimum of the function q will be found at or before the nth step, irrespective of the starting point. Okay, now we will explain what is the algorithm of Powell's method. The basic idea of Powell's method is illustrated graphically for a two-variable function in figure 6.8. Actually, these circles like, not actually it is not circles, these are what yes, elliptical in shape or something like that. So these curves, these we will call contours, not circle, not ellipse, and these are called contours, contours. So these contours are our objective function f of x. Okay, so what is happening to this objective function f of x? This this objective function f of x is getting minimized, so that it is minimum at this point, and the corresponding coordinates, corresponding x1 x2, we are calling it as optimum values. Okay, optimum values. So our objective is this. Now this is the progress of Powell's method. Okay, so in the Powell's method, first of all, algorithm we are discussing. So for algorithms, you blindly follow the algorithm, then you will reach the minimum point. So and we will understand. If you understand the algorithm, then it is easy to apply also. So we will try to understand the algorithm first. Okay, yes. So in this figure, that means this figure 6.8, in this figure, uh, for any unconstrained optimal problem, we should choose an initial point x0, okay, and that x0 or x1, you can say x1, that x1 is this one. Okay, this is our x1. So initial value, and yes, along, and first of all, in the Powell's method, first what we are doing is we will have a univariate search first. That means we will minimize the function once along each of the coordinate directions, starting with the second coordinate direction. That means we will search in the coordinate directions. Here x1 x2 are the coordinate directions, that is u1 u2. Let us say u1 is parallel to u1 is the unit vector parallel to x1, and u2 is the unit vector parallel to x2. So in Powell's method, we will search in these two directions, u1 and u2, first of all, u1 and u2 direction first of all. Okay, and here we are starting with the second coordinate direction, that is u2. Okay, and then in the corresponding pattern direction also. That means, yes, first we have x1, okay, and we will continue the search in x2 direction, in this direction. That means we will have the direction parallel to x2 direction, that is u2 we will have. So we will have direction, we will be getting plus direction or minus direction. Okay, first you got the direction, then the next point is how far you have to go in that direction, so that our function f of x, that is so that our contour contour is having the minimum value, or contour is minimized. Okay, so that so in that manner, then so that you have to find out the another term, that is step length. Step length, that means how far go you have to go in, you have to search in that direction, that particular direction. So that we will find out, which is already discussed in the univariate method. We have discussed that so you refer that. So in this direction we have searched first, then we will go in the second coordinate direction, that is parallel to x1 axis, that is in this direction we will go. So in that step also we have to find out the optimum step length, that is lambda star. Okay, and also you have to you should determine, or you should identify that plus x1 direction or minus x1 direction you have to go. That means in this direction or in this direction you have to go, so that the contour is getting minimized. So in this figure it is very much clear that if you go in this direction, that is minus x1 direction, what happens is the contour, yes, the new contour will be like this. Okay, that means the contour is getting big, a bigger contour, so the minimization will not be possible. So the conclusion is the opposite direction, that is in this direction, so that the contour is minimized, size is minimized. Okay, so the yes, that is what the algorithm says, that is for in the Powell's method, first the function is first minimized once along each of the coordinate directions. Each of the coordinate directions we will minimize the function, starting with the second coordinate direction, that is starting with the x2 direction. Okay, that means x towards, or in the x2 direction we will minimize the objective function, and then we will minimize the objective function in the x1 direction. Okay, and then we will apply the conjugate direction theorem. Conjugate direction theorem, that is if we have two hyperplanes h1 and h2, that means we are considering two hyperplanes h1 and h2 like this. Okay, h1 here and we have, sorry, not this is not the hyperplane we have to consider. Yes, we have to consider the hyperplane like this. Yes, this is our hyperplane. Okay, this is our hyperplane h1 and h2, and also we have the two optimum solutions here. Okay, this 2.2 and 0.4. Okay, it lies on the hyperplanes h1 and h2 respectively, the 2 and 4. That means this is x1, this is x2, and this is x3, and this is x4. Okay, so what the first theorem, that is theorem 1, says that given a quadratic function of n variables, here 2 variables, and 2 parallel hyperplanes h1 and 2, that is h1 and h2, of dimension k less than n, that means of dimension, it is having a dimension 1 which is less than 2, then the constrained points of the quadratic function, okay, it is given as a s function in the hyperplanes are x1 and x2 respectively. Here such points are here x4 and x2, x4 and x2, x4 and x2, okay, because x4 is the final point and x2 is the final point or the new point in this hyperplane h1. So the latest points are we are taking the latest points only. So x2 and x4, okay, instead of x1 and x2 respectively. Then what this theorem says, then the line joining x1 and x2 or x2 and x4 is the conjugate direction to any line parallel to the hyperplanes. So that means, okay, the line joining x2 and x4, that is this, will be our conjugate direction, okay, the conjugate direction, and which is also known as first pattern direction, that is denoted as sp1. Okay, yes, so we found the first pattern direction or the first conjugate direction, okay, and this pattern direction, as a result of this pattern direction, it is by theorem 2, it says that if we go in this direction, in this conjugate direction, from x4, from the point x4, okay, then you will get the minimum, you will get the optimized value for f of x. That is what the theorem, second theorem says. But how far you have to go, okay, and it is in whether it is in positive direction or negative direction, that you have to decide. Okay, so it is found that it is conjugate direction, it is in positive direction, you have to go. So from x4, yes, a conjugate direction, we will search in this conjugate direction, and we have reached to this point 5. Okay, so that this will be the new objective function, that is minimized objective function, like this. Okay, fifth point. So yes, so the first pattern search is over. Then for the next cycle of this, that means, yes, that will lead to the point 5. Then for the Powell's method says that you have to choose for the next cycle of minimization, what you have to do is you have to discard one of the coordinate directions. That means instead of going, okay, instead of going initially in x1 direction and then in x2 direction, you can directly go from this point to this point like this, that is in the conjugate direction. So that means you should discard one of the coordinate directions. Okay, here in this case the x1 direction is discarded, okay, is discarded. So yes, so in that way we will continue our next cycle, okay, next cycle of iteration. That means now onwards, that is from point 5, okay, that is from point x5 onwards, we will eliminate or we will discard the x1 direction, and we will have two directions, that is x2 direction or u2 direction you can say, and another the pattern direction sp1. Okay, so thus we will minimize along u2 and s1, that is s1 means sp1 that is first pattern direction, and we will obtain the point 7 like this. That is, from x5 we will optimize in u2 direction or in x2 direction, and we will get x6. Okay, and then we will minimize the objective function in the first pattern direction, that is in this direction, that is this. We will draw a parallel line to this like this. Okay, yes, and then we will reach in 7th, that is x7 position. Okay, then we will generate a new pattern direction, that is s2 or sp2. This s2 is equal to sp2 as shown in the figure. That means, yes, let me erase, sorry, yes, let me erase. Yes, we have reached the here 7th position. Okay, and then okay, and in this cycle, that is cycle from x5 to x7. Okay, in this cycle we have got a new pattern, a new pattern direction, that is sp2, that is here. This is the new pattern direction. Okay, that means yes, that means this will be the new conjugate direction. For conjugate this to be conjugate directions, okay, we should have the the two hyperplanes h1 and h2. Okay, h1 and h2 like so. In order to generate the second pattern direction, that is sp2, or the second pattern direction, or the second conjugate direction, you can say second conjugate direction, again we should have two hyperplanes, that is h1 and h2. So earlier the two hyperplanes was like this, right? Okay, like this, h1 and h2. Okay, and this is x2 and this is x4, and we got the first pattern direction or first conjugate direction as x4 minus x2. Right, now we have the again the hyperplanes, two hyperplanes we are defining like this. Yes, this is h1 and this is h2. This is h2, and the latest point on this h1 will be this. Okay, this x5, right, x5, and here on h2 it will be x7, so that we got another conjugate direction, right, and another conjugate direction, that is x7 minus x5, and it is directed from x5 to x7 like this. Okay, now that indicates that if you find out the conjugate direction, then it is simple that in the next step you should go in this conjugate direction. That's all. Okay, so what has happened here is from 7 to 8. Okay, uh, from 7 to 8 the search is gone in this direction, in this direction, right, in this direction, so that we reached here 8th position. Okay, in eighth position. Now from 8 actually from 8, uh, if we have another coordinate direction like x3 or x4, like x3 for example, then you have to discard x2, and you have to choose this x3 and another pattern there, pattern uh, and not another, the previous patterns or sorts previous conjugate directions. You have to do like that. But here only x1 and x2, x1 and x2 two coordinate directions are there, and x1 is eliminated previously, and x2 recently it's been eliminated by the conjugate direction sp2. So we have no other coordinate direction to eliminate. So we should uh, continue our search in first of all in sp1 direction, and then in sp2 direction, so that you will get 9. Yes, so that you will get this 9, that is x9, and you got x10. Okay, yes, that is what this this point is saying. That is then, yes, that is then we generate a new pattern direction, that is s2 or sp2 as shown in the figure, for the next cycle of minimization, and we discard one of the previously used coordinate direction, that is x2 direction in this case, in favor of the newly generated pattern direction. And then by starting from point 8 we minimize along direction sp1. Actually this s1 is sp1 and sp2, thereby obtaining points 9 and 10 respectively. Okay, then for the next cycle of minimization, since there is no coordinate direction to discard, that is x1 is discarded, x2 is discarded recently, so we have no other coordinate direction to discard, then we start the whole procedure by minimizing along the x2 direction. That means we will again repeat the minimization procedure in this direction from x10, that is from x10 we will search in this direction, and this in this direction, and again that whole thing is repeated, so that this point, minimum point, is reached. Okay, so that is what our algorithm for our Powell's method. Now we will solve an example problem so that you will understand better. Now, yes, this is our objective function, that is minimize f of x1 x2, where that means x will be equal to x1 x2, that is dimension, having dimension 2, and it is equal to x1 minus x2 plus yes, this equation. Yes, from the starting point, yes, the starting point should be given for any unconstrained problem. So the examiner has given the starting point x1 0 0, or if the examiner is not given, you should take it as x1 equal to 0 0. Using Powell's method, you have to solve this. So yes, so in cycle 1, yes, what the Powell said in Powell's method, what he has said is that you should go in the uh, yes, in the coordinate directions. In the coordinate directions. Here in this example, the coordinates are x1, x2. So you should go in x1 direction as well as in x2 direction first and then x1 direction. So for this you should use the univariate method, univariate search method. That means we minimize f along S2, that is where S2 is taken as 0 1, okay, from x1, and to find the correct direction plus S2 or minus S2, yes, the same step what we have discussed in a univariate method, okay. Whether it is plus S2 or minus S2, we have to check. For that we will consider a problem length epsilon equal to 0.01, and we will evaluate f of x1, okay, and then f plus we will evaluate, and we will evaluate f minus also, okay, and this f plus is found to be less than f1, and okay, so the direction means f decreases along the direction plus s2. It is sure that it is seen that f decreases along the direction plus s2. So our direction will be plus s2. Okay, now the next step is to find how far you have to go. That means the step length, that is lambda star. So f of x1 plus lambda s2 we will calculate, that is f of 0.000 comma lambda, so that we will get a function in degree 2, a quadratic polynomial lambda square minus lambda, and for in order to get lambda star, that is the optimum solution, we will use the Newton's method, that means df by d lambda equal to 0 and d square f by d lambda square will be less than 0. So less than 0 or greater than 0, sorry, greater than 0. Why? Because yes, then only the lambda will be a point of minimum function value. Then yes, we have x2, okay, so lambda star will be equal to 1 by 2. So we got lambda optimum value 1 by 2, and also s direction, and then from univariate method we will find out the x2 value, okay. So if you have any doubt, you go back to that method, univariate method, okay. Then the x2 equal to x1 plus, yes, you got this x2, okay, and next is we will minimize in s1 direction or in x1 direction, okay, and yes, then we found the x3, okay, x3 we got. Now again we will minimize in x2 direction, that is what the Powell said, that is yes, okay, that is first in x2 direction, then in x1 direction, then again in x2 direction, okay, so that so that one conjugate direction, a conjugate direction like this is obtained. Okay. Yes. Okay, so we got the x3 and we got x4. Okay, we got this x4. That means we have reached at this optimum solution point. We have reached here. Okay, now yes, now what is the next step? Next step is cycle 2. Next cycle. Okay, in which we will get a pattern search or a conjugate direction sp1 denoted by sp1, and that sp1 will be equal to x4 minus x2. Okay, and this already we have discussed. Now what we have done in Powell's method is we will go in cycle 2. In cycle 2 we will go in this direction, in the sp1 direction. Okay, that is what this, yes, f4, we have found sp1 and we found f4, then we have found f plus and f minus, in order to find out the direction, whether it is plus sp1 is minimizing the objective function or minus sp1 is minimizing the objective function. So it has got that plus sp1, that is positive direction of sp1 is minimizing the objective function. So we choose that, and we got also we got this in terms of lambda, and we will optimize lambda by Newton's method, that is df by dA lambda equal to 0, and we will solve for lambda. That will be the optimum point for optimum value for lambda, that is denoted by lambda star. Okay, and if you find out lambda star and yes, then easily you can find out the next optimum solution, that is x5, that will be equal, that is given by this formula. Okay, and the point x5 in this problem, the point x5 is identified as the optimum point. Why? Because beyond x5, okay, beyond x5, what we have to do is, beyond x5 you have to go the search, you have to continue the search in direction of x2, so if you go in the direction of x2, okay, x2, in the direction of x2, then it is found that the objective function is maximizing. Okay, that means f plus is greater than f5 and also f minus is greater than f5. In either direction the objective function is maximizing instead of minimizing. So we will stop our pattern, or we will stop our search in at x5, and we will declare this point x5 is identified the optimum point. Okay, so this is our entire discussion all about our Powell's method. So Powell's method is over. Thank you.